So welcome to chapter 10. This is about rotation, and this will be sections 10.1 to 10.5 in the textbook. And really the way of thinking about this particular section is that it's rotational kinematics.
All right. Oh, Chris.
And that was my door. And so first thing we need to do is relate rotational to translational motion. And we know that centripetal acceleration is v squared over r, and it's also r omega squared, and omega is lowercase that we use here. It's the last letter of the Greek alphabet, and that stands for the angular velocity, right? And when we do the angular velocity, all this stuff, we're doing things in terms of radians, not usually degrees, although you will see relating degrees to radians at times. So when we're relating angular to translational, we've got to keep in mind that we now have three different types of acceleration. First of all, we have the tangential acceleration. So if this thing is speeding up as it spins around, then it may be accelerating parallel to the velocity. We have the radial or the centripetal acceleration, right? It's another way of, two different ways of referring to that. And that's v squared over r. So that's AR or AC. And then we also have alpha. Alpha now is the tangential acceleration divided by the radius. So A tan is R alpha. And alpha is the angular acceleration. And that's measured in radians per square second. And you can see that if we take the tangential and the radial acceleration, that gives us the total linear acceleration. So the result is actually a vector sum of the tangential and the radial acceleration. Radial centripetal acceleration always points towards the center, like we've already kind of talked about. Using the example here see if you're on a merry-go-round, if you're near the middle or the outside, where do you go faster? You go faster if you're around the outside. So there your linear speed is more, although your rotational speed is the same because you're covering the same angle, right? The same change in angular location, no matter where you are on the merry-go-round. So in other words, the angular speed does not depend on where you are on the merry-go-round, but your linear speed does. Okay. So to do rotational problems, it's actually really simple. We keep the same equations that we had before. We use VF equals VI plus AT, delta X equals VIT plus 1/2 AT squared, all of our VIF-TAD equations, and all we do is we translate them into Greek. Okay, so you can see that delta theta replaces position. So we have angle now instead of location. And omega replaces v. And alpha, which is angular acceleration, that replaces a in our VIF-TAD equations. But t remains the same. And so you can see these equations, right? VF equals VI plus AT becomes omega F equals omega naught plus alpha T. And instead of delta X equals VIT plus 1/2 AT squared, I've got delta theta equals omega naught T plus 1/2 alpha T squared, and so on. So when you read these problems, think of them kind of as linear. Think of the linear kinematics VIF-TAD equations you would use, and then it can become, just translate it into Greek. And so VIF-TAD becomes WIF-TAF. You get omega IF T alpha theta. So we get WIF-TAF. In example 1, we are given that omega as a function of time is omega naught e to the negative kt. And then we're given the angular velocity at a couple of spots. That omega at 0 is 3.5 radians per second, and omega at time 9.3 seconds is 2 radians per second. Okay. And now the first thing we need to find omega naught and k. Well, first of all, we know that omega at time 0, if we plug 0 into this, we get omega naught e to the negative k times 0, but that makes this just 1. And so this is omega naught. And now we know omega at 0 is 3.5. So now we know what omega naught is. And now we want to find what k is. So can we do that? So we use this other equation, omega at 9.3 seconds is 3.5 e to the negative k times 9.3. And that we know is equal to 2, because omega at 9.3 is 2. So e to the negative k times 9.3 equals 2 over 3.5. Take the natural log of both sides, so negative k times 9.3 equals natural log of 2 over 3.5. So k is equal to negative 1 over 9.3, natural log of 2 over 3.5. And that gives you a value of 0.0602. And what are the units on that? That's interesting, right? Well, if it's being multiplied by t, multiplied by time, I can't have any units left over in the exponent. And so this has to be 1 over seconds. So the seconds cancel out. And so this has a unit of 1 over seconds. And omega is in radians per second, obviously. So now part B. Sketch omega t versus t. So here's B. This will be omega. This is t. At time 0, we're at 3.5. So, and what's happening here, you can see that it's slowing down over time. And we know what it looks like because we've seen this type of graph before. It's going to be something like this. So this is 3.5. 2 might be somewhere around here. So this is 2. And this would be 9.3 seconds. So that's what omega versus t is going to look like. C, find the angular acceleration as a function of time. Now, remember that omega is just angular velocity. It's like v. And so how do we find acceleration from velocity? We take the derivative with respect to time. So alpha is going to be d omega dt. So d dt of 3.5 e to the negative 0.0602 times t. Take the derivative of that, and this gets brought down, right? We multiply by that. So this ends up becoming negative 0.211 e to the negative 0.0602 t radians per second squared. And that's our angular acceleration. And now we want to find the angular acceleration at 3 seconds. So A at 3 seconds, put that, A at 3, or alpha at 3, is going to be, we plug 3 seconds into this, 0.211, negative rather, e to the negative 0.0602 times 3, right? This is just plug and chug, plug the number in. And we should get negative 0.176 radians per second squared. What does this mean? The negative. This means that the acceleration is in the opposite direction of the positive direction for the angular velocity. Because the angular velocity you can see is positive, right? It's above 0. And so that means it's slowing down. And positive is counterclockwise, so that means the acceleration is in the clockwise direction. Slowing it down. And so the E, this graph I'll put here. Since it's negative, we'll go alpha time in seconds. This is in radians per second squared. This also, because we've seen graphs like this, we know it's going to have that type of value to it. And at time 0, this is the acceleration, so negative 0.211. That's the acceleration there. And then after 3 seconds, maybe it would be about here. And the angular acceleration there is negative 0.176 radians per second squared, and that's at about 3 seconds. Next one, now we want to find the angular displacement as a function of time. So that's theta. Theta is a function of time. And now this is going to be the integral of the velocity, right? This is how we go from displacement or from velocity to displacement, take the integral. So I'm going to take the integral of this, integral of omega t dt. So that is going to look like this. We're going to go from 0 to any later time t of our function, which was 3.5 e to the negative 0.0602 t dt. So that's going to look something like this. Or I can bring the 3.5 out front. Maybe that'll make it a little bit simpler for you. E to the negative 0.0602 t dt. And so what I get is 3.5 over negative 0.0602 e to the negative 0.0602 t from 0 to sometime later t. When I plug those numbers in, now I end up with, just keep going this way, 3.5 over negative 0.0602. T goes in, and it just remains there. So that would be e to the negative 0.0602 t minus, when I plug 0 in, that's 1, this. And then I can flip the order and kind of put the negative sign in. And so I have 3.5, 0.0602, 1 minus e to the negative 0.0602 t. Okay? And this becomes 58.1. So we can simplify that a little bit. And so what does this mean? That means that it's, it's moving in the positive direction, so it's gaining positive displacement in the clockwise or the counterclockwise direction as it's going around. And this is the maximum angular displacement that it's going to have in radians. And so we want to know what is the position at 3 seconds. Well, we just plug the numbers in, right? 58.1 times 1 minus e to the negative 0.0602 t. Or rather, sorry, we're plugging in 3. And that gives us 9.6 radians. So that was G. This was F. Apologize. H. Want to see what the graph looks like? We've seen this type of graph before. This is going to reach some asymptote, and the asymptote especially is going to be 58.1 radians. So this is theta in radians. This is 58.1. Somewhere down here, we're going to have 9.6 after 3 seconds. So it looks something like that. So this is 3 seconds, 9.6 radians, and then approaching 58.1 radians. And that's example 1. Example 2. This one is kind of a real-life type of problem. You have a grindstone, the radius is 0.5 meter, and it has a constant angular acceleration of positive 3 radians per second squared. A line connects the center C of the grindstone to a point P on its rim. When the grindstone starts rotating from rest, the line CP is horizontal. So what are we saying? Well, let's draw a picture of this, kind of get an idea of what's going on. There's a line C. It's initially horizontal, this line connecting the center and point P. It has a radius of 0.5 meter. And it starts rotating from rest, and we're given the angular acceleration. A is 3 radians per square second. Okay. And omega naught is 0 radians per second. And initial position, since it's like this, we can consider that initial angle theta as just 0. So what are we looking for? Well, in A, we're looking for the number of radians swept. What is that? That's theta. Not equivalent to, but analogous to displacement. Then I'm looking for omega in part B. Part C, I'm looking for V, right, the speed of point P. D, I'm looking for the tangential acceleration, so that's A tan. E comes after D. Then I'm looking for the radial acceleration, so that's the centripetal acceleration, right, this acceleration towards the center. A tan is the tangential acceleration going up that way. And F, looking for the magnitude of the total acceleration of point P. So I'm looking for that, which is a combination of tangential and centripetal linear acceleration. Okay. So let's do this. If I had, these are the things I know, and this is the given information. So think about it this way. If you wanted to find position at some later time, and you had acceleration and you had time, right? I know the time I'm looking for is at 2 seconds. Is that right? And I want to know the position at some later time based on the acceleration and the initial velocity and all that stuff. So for that, we would use delta x equals VIT plus 1/2 AT squared. Constant acceleration, so we can think of this in terms of VIFTAD, except WIFTAF, right, because it's Greek now. So theta equals omega naught t plus 1/2 alpha t squared. I just replace v with omega, v naught with omega naught, and a with alpha, and I get this. So I plug my numbers in. This is 0. Omega naught is 0. So it's 1/2 times 3 times 2 squared. I'm going to get 6. 6 radians. For omega, I'm looking for omega f. Right? So if you were looking for the final velocity, probably vf equals vi plus at. So this would be omega f equals omega naught plus alpha t. This is 0, goes away. Alpha is 3 radians per second squared times t, which is 2 seconds, 6 radians per second. Okay, this is a coincidence. They're not always going to be the same. It's just a coincidence this time that happened. Okay, the velocity. How do we relate velocity and angular velocity, linear and angular velocity? Well, r omega. R, I know, is 0.5. It's half a meter. And omega at this time, right, at 2 seconds, is 6 radians per second. Okay. So half of this would be 3 meters per second. Pay attention to the units, right? Here's one of those crazy places where radians just kind of disappears. You multiply radians by meters, and radians go away. D, the tangential acceleration. How do we get tangential acceleration? Well, that's our alpha. So again, 0.5 meters is the radius times the angular acceleration of 3 radians per square second, and I get 1.5 meters per second squared. That's how we convert. And then the centripetal acceleration is v squared over r, or omega squared r. Right. So either way, let's use this one since we have omega. Well, we have v. Doesn't matter really. So omega squared r. Omega at this point is 6 radians per second. We square that times r, so it's half a meter. 36 and a half. 36 is 18 meters per second squared. Okay. pay attention to the units, you get seconds squared here, radians squared, but we don't really care about the radians. Multiply by meters, and we get meters per second squared like we want. Okay, now this one, total acceleration. If I look at the position, right, I'm at about 6 radians. So that means I'm about maybe here or so, somewhere down in there. And so the velocity is this way. This is going to be the direction of the tangential acceleration. The centripetal acceleration is pointing in towards the center. And so I'm looking for the direction of the total acceleration. So it's going to be somewhere in this direction will be a total. I don't care about the direction I'm just looking for this. So how do I do that? Well, I just do Pythagorean theorem to get the magnitude. Again, don't care about the direction. So the magnitude is going to be the square root of 1.5 squared plus 18 squared. And I believe that gives you 18.1 meters per second squared. It's almost equivalent to the centripetal acceleration. And angular quantities are considered to be vectors, right? But they're vectors rotationally. And so we can have a vector that points around a direction in the, in the circle. And so remember the right-hand rule, right-hand coordinate systems, we talked about those. Well, now we have our first right-hand rule. And so just kind of to practice, number one, that first one there is going around in the circle. So if I have a vector like this, right, the result is the thumb pointing out using the right hand. So for one, looks like that. Two, the opposite, right? The hand is curling this way, in the direction like there. Then the thumb points in. So the answer kind of looks like that. Three is a little tough to kind of see. What's happening there is you've got the dot on top and then the X on the bottom. So it looks like this. Into the board here and out that way. So for 3, you're going into the board here and out, right? This is pointing in, this one's coming out. So it goes that way. You imagine your hand kind of going in a circle like that. 4, here you're coming out of the board on the bottom and into the board on the top. So you imagine a circle here, right? This is a circle, this is a circle. And here you're going in like away on the top and towards you on the bottom. So when you do that, your thumb points to the left. So that's the answer for that one. 5, same kind of thing. We've got a circle coming out of the board this way. It's going in on the right and out on the left. So here you're going in and here you're coming out. This one's pointing towards you. So your hand is going like this. Your thumb is pointing up. So up is the result. And then 6 is we switch these. So here you're coming, this one's not easy for me to do with my right hand, but you're coming out on the right and in on the left. So it would be like this. Here we go. This is how it is. You're going like this. So your thumb is pointing down. And that's the result. And we're going to use that again and again. And of course, the danger is that when you're taking the AP test, the proctors might think that you're throwing up gang signs because you're moving your hands all the time. But you've got to. If you're doing these problems and you're not moving your hands, you're doing them the wrong way. So make sure you just use your hands. You look crazy, but you'll get the problem right. And then when we get to the end, since we are still dealing with vectors, if I have something rotating, then it has direction. And so if I have something rotating this way, I use my right hand rule. I curl my hand in the direction of the rotation, and the direction that my thumb points, we can use that as saying the direction of the rotation. So if something is rotating this way, it's going that way. And so in that last example, that final direction, that is one way we can specify the direction of the rotation, and that is a right hand rule.